Good afternoon, everybody, or morning or evening. Welcome back to the fourth installment of Waves. Hope you've enjoyed everything up to now. Today, what we're going to talk about is waves that are in tubes or on strings. Also, this is called harmonics. Today, you will not need your equation sheets, which is absolutely wonderful. But colors are probably going to be pretty important today. We're going to do a lot of drawing. So today you're definitely going to have to be pausing and drawing and writing. I'm not going to write everything on the notes today. So just a little FYI about that. Okay, here we go. We're going to start this with strings to begin with because they're a little bit easier. So we're going to talk about how waves go on strings. Now, if I pluck a string, it's going to vibrate like this. And it's going to be going up and down in the middle. And on the sides, it's going to be stuck. Now, this works for a guitar, a piano, anything that you pluck. It'll do this. Let's label a few things. We've got the nodes. The nodes are where the string doesn't move. Those are at the end. We have a crest and the trough. Notice for this string, the crest and the trough happen at the same spot on the string. It goes up and down there. So first it's at the top, the crest, and the trough. I'm going to change those two words into one, though. So we're going to call those antinodes. So the antinodes, in this case, are right there in the middle of the string, and the nodes are on the sides. All right, so you should label those so you know where they are. It's nodes, antinodes, and strings. The last thing on here that I'm going to put is I'm going to label the length from one spot where the string is at one end to the other as the length, capital L. So that's essentially the length of the string. The string, I guess, stretches a little bit when you pluck it, but we're going to call it L for length. All right. Here's what we're going to figure out. We're going to figure out how the length relates to the wavelength of the wave on the string. So what I've done next is I've drawn, if the string were longer, okay, what it would look like. So I've just drawn it when in our real section it's at the top, then it goes down, and you can see it going back up off to the right of the screen here. If you look, let's see if we can figure out how long a wavelength is on this. So I want you to have a peek here at the left end of the string, right here. Okay, it is now at a node, but it's going upwards. Okay, as we move to the right, the string is pointing up a little bit, if you will. Follow the string along until you get to the next node. Now be careful, that's not a wavelength because it's going down now. Wavelength is back to the same spot on the string. So to get to a wavelength, we have to go all the way out over to here. Can you see that it's at a node again and it's going up? So what I can do is I can draw on here that this equals one wavelength. All right? That wavelength then is twice the length of the string in this case. So for my when I pluck a string like this, the length, okay, or actually I should say two lengths equals one wavelength, or the length equals half of a wavelength. Just move the two to the other side. All right? I want you to put a big arrow towards this. Now, for a string, that equation works for the fundamental wavelength. That's what this is called, the fundamental. It's also called the first harmonic. So that label should be all around these pictures. When a string wiggles like this, it's called the fundamental. It's also called the first harmonic, and the wavelength is twice the length of the string. Okay? So again, I didn't write all that down. I'm expecting you to do that, and I'm going to keep moving. So pause me, and when you're done, we'll keep going. Alrighty. The next thing that could happen with the string is it could vibrate like this. So instead of the whole string wobbling up and down in half of a wavelength, could you see here that half of it's moving up and half is down? All right. As the part on the left is going up, the part on the right is going down, and vice versa. Okay, let's do our same equation, see what we can figure out for this. This one is a little easier. Can you see that we have exactly one wavelength fitting into the string there? So what we've got is the length of the string equals exactly one wavelength. This is called the second harmonic. All right. One more here. Go down to here. This is the next way it could wobble. Okay. What I'd like you to do is see if you can write the relationship between the length of the string and the wavelength. Okay. This one is a little tricky. See if you can do it. I'll see if I can do it, for that matter. I'm not even sure I can. So let's say the length of the string and the wavelength, I'm going to write those down. Now, looks to me like one wavelength plus a half fit inside the length. So there's one wavelength right there. Can you see that? So we have one wavelength plus another half of a wavelength equals the length of the string. 1.5 wavelengths is 3 halves of the wavelength equals the length of the string. All right. Now this is a perfect example of an AP question. All right. They'll give you the length of the string and they'll say, write down the wavelengths of the fundamental, the second harmonic, and the third harmonic. All right. And the second or the third are the ones I just did. Okay. So next up, tubes. Here we go. For a tube, there's two kinds of tubes. One that's open at one end, one that's open at both ends. That's what you're going to see. Here's the best way to tackle tubes. Okay, I draw a picture and I put a dotted line right down the middle. That helps me. I want to figure out the fundamental wavelength that will resonate or ring in this tube. Organ pipes are made this way. The boom whackers that we have in class, we can put a cap on the end and we'll do that and you can see how they work out. So here's how I look at this. I look at the left end and I say, now the left end is closed. Air is not allowed to move back and forth there. So that has to be a node, just like the string. Okay? It's like a piano string or a guitar string. But the right end is open. At that end, the air is going to move as much as it can. Okay? So that's going to be an antinode. It's going to go from the top to the bottom when we draw the wave. Okay? So as I think about this, I go, okay, I have to draw my wave in this one, and the wave has to touch the middle on the left side, but on the right side, it's got to touch the top and the bottom. So I actually make little dots there to help me do that. And then I say, okay, let's draw a wave that'll fit that. And I want to draw the wave that has the least number of wiggles. Well, the least number would go like that. Kind of gave it away here by opening up the rest of the page early. But that's what it looks like. You go, okay. So then step 2 is, after you draw that, let's keep going. Keep going with the wave. And so I've extended my dotted line, and I've doubled the length of the tube. I've kind of guessed at that. And then I bring the wave back down to the node again. Can you see that? Now, if we look back to the very beginning, one full swing. I'm going to switch up to our string again. All right. Looking back at this guy. All right, see the string? We have one loop up and back to the node. All right, and that is half of a wavelength. So jumping back over to here, this entire thing is half of a wavelength. Okay, so the length of the tube in the top picture here is only actually holding a quarter of a wavelength. So let's write that. The length of the tube, oops, sorry, I didn't even label that for you. The length of the tube equals 1/4 of the wavelength. All right? How'd we do with that one? Once again, you should be writing the words fundamental and first harmonic all over this. Let's look at the next one. The next thing that could happen is in this same tube, it could wobble from 0 there, from a node, and the end again needs to be an antinode, but it's going to go up to the top this time and then back to the bottom. Notice I went from the middle to the top before. Now I need to go up and come back down and get to an antinode. Okay? This one is the second harmonic. Can you see that? So label second harmonic all over this, and let's see what the length of the tube is. So once again, I'm going to draw my wave, whoops, it's in blue, back up to a node, right? Let's draw a length right there. Now, where's my wavelength? All right. Hey, check it out. That's exactly one wavelength that I've drawn. So that wavelength is a little more than the tube. Okay? The tube is only actually reaching 3/4 of a wavelength. So the length of the tube, whoops, I was writing that in red. The length of the tube equals 3/4 of a wavelength. Wow, I'm going way too long. We're going to have to break this up. Let's go down to the next one. Whoops. I did that. Guess we'll have to go to the next one on the next slide. There's the next one. This one is the second harmonic. Can you see I've gone from the center on the left, from the node to an antinode again. But now I've done one more wiggle of the wave. The second harmonic. I want you to see if you can write down what the equation is. If it would help, go ahead and continue the wave back down to the node. All right? And see if you can do it ahead of me. So pause it, see what you can figure out. Alrighty, so for me, I look at this and there's 1.5 wavelengths all the way out to here. Alright, 1.5 wavelengths, but the 1.5 wavelengths isn't the whole length of the tube. The length of the tube is a little less than that. It's less by 1/4 of a wavelength this time. Oh my goodness. 1.5 is 3/2 or 6/4. But I want one less than that, so we end up with 5/4 of a wavelength. All right. Now that one is a little tough. All right, I've got to get out of here. This is taking way too long. So I'm going to speed up a little bit, so hang on. The next one is an open tube. Open tube, here we go. You're going to need to pause me a bunch. In the open tube, I need to have my wave hit the ends and do an antinode at each end. So I've got to start here at the bottom, and I'm going to end here at the top. So I'm going to go through the node and end up at the top. And here's my dotted line down there. Okay? So now, if I'm kind of getting the hang of this, that's a quarter of a wavelength. So for this one, the length of the tube equals a quarter of a wavelength. So far, so good. How do we do? All right, I want you to do the next one. Step 1, draw the dotted line. Step 2, draw the dots where your wave has to go. And step 3, connect them. All right, pause me and do that. Welcome back. Here we go. There's my dotted line. There's my antinodes. And you get to laugh at my drawing here. I need to go up and back down. Hey, check it out. How about that one? For this one, the length of the tube, can you do the math? Do it all yourself. Pause me and then move on. The length of the tube is going to be 1 wavelength exactly. All right? See if you can do this one. I'm going to leave that up to you. I'll give you the answer in class. But let's skip right on down to your homework. So here's your homework. I want you to find the fundamental frequency, which is the first harmonic, and the second harmonic for the following situations. A string, a tube open at one end, and a tube open at both ends. I'm giving you the length now. The length of each one of those is 1 meter long. So for a 1 meter string, find the first and second harmonic for a 1 meter tube open at one end and a 1 meter tube open at both ends. I'm sorry I took so long, folks. That was awful. Hopefully, you're not too mad at me. Have a wonderful day.